Hello, wonderful audience. Thank you for choosing to spend your time with me. Welcome, everyone, to our latest video where we'll be exploring Grothendieck topology. In category theory, a branch of mathematics, a Grothendieck topology is a structure on a category Celsius that makes the objects of Celsius act like the open sets of a topological space. A category together with a choice of Grothendieck topology is called a site. Grothendieck topologies axiomatize the notion of an open cover. Using the notion of covering provided by a Grothendieck topology, it becomes possible to define sheaves on a category and their cohomology. This was first done in algebraic geometry and algebraic number theory by Alexander Grothendieck to define the étale cohomology of a scheme. It has been used to define other cohomology theories since then, such as ℓ-adic cohomology, flat cohomology, and crystalline cohomology. While Grothendieck topologies are most often used to define cohomology theories, they have found other applications as well, such as to John Tate's theory of rigid analytic geometry. There is a natural way to associate a site to an ordinary topological space, and Grothendieck's theory is loosely regarded as a generalization of classical topology. Under megapoint set hypotheses, namely sobriety, this is completely accurate, yet it is possible to recover a sober space from its associated site. However, simple examples such as the indiscrete topological space show that not all topological spaces can be expressed using Grothendieck topologies. Conversely, there are Grothendieck topologies that do not come from topological spaces. The term Grothendieck topology has changed in meaning. It meant what is now called a Grothendieck pre-topology, and some authors still use this old meaning. Modified the definition to use sieves rather than covers. Much of the time this does not make much difference, as each Grothendieck pre-topology determines a unique Grothendieck topology, though quite different pre-topologies can give the same topology. In the next segment, we'll be exploring overview and its implications for our subject matter. Andrew Wiles' famous wheel conjectures propose that certain properties of equations with integral coefficients should be understood as geometric properties of the algebraic variety that they define. His conjectures postulated that there should be a cohomology theory of algebraic varieties that gives number-theoretic information about their defining equations. This cohomology theory was known as the wheel cohomology, but using the tools he had available, Wheel was unable to construct it. In the early years, Alexander Grothendieck introduced étale maps into algebraic geometry as algebraic analogues of local analytic isomorphisms in analytic geometry. He used étale coverings to define an algebraic analogue of the fundamental group of a topological space. Soon Jean-Pierre noticed that some properties of étale coverings mimicked those of open immersions, and that consequently it was possible to make constructions that imitated the cohomology functor. Grothendieck saw that it would be possible to use Serre's idea to define a cohomology theory that he suspected would be the wheel cohomology. To define this cohomology theory, Grothendieck needed to replace the usual topological notion of an open covering with one that would use étale coverings instead. Grothendieck also saw how to phrase the definition of covering abstractly. This is where the definition of a Grothendieck topology comes from. As we enter this new phase, let's analyze motivation from different angles and evaluate its significance. The classical definition of a sheaf begins with the topological space X. A sheaf associates information to the open sets of X. This information can be phrased abstractly by letting X be the category whose objects are the open subsets U of X and whose morphisms are the inclusion maps V U of open sets U and V of X. We will call such maps open immersions, just as in the context of schemes. Then a presheaf on X is a contravariant functor from X to the category of sets, and a sheaf is a presheaf that satisfies the gluing axiom here, including the separation axiom. The gluing axiom is phrased in terms of pointwise covering, i.e., UI covers U if and only if IU. In this definition, UI is an open subset of X. Grothendieck topologies replace each UI with an entire family of open subsets. In this example, UI is replaced by the family of all open immersions VIUI. Such a collection is called a sieve. Pointwise covering is replaced by the notion of a covering family. In the above example, the set of all the IUIJ as I varies is a covering family of U-sieves, and covering families can be axiomatized. And once this is done, open sets and pointwise covering can be replaced by other notions that describe other properties of the space X. Let's now turn our gaze towards sieves and explore the fascinating connections it has to offer. In a Grothendieck topology, the notion of a collection of open subsets of U stable under inclusion is replaced by the notion of a sieve. If C is any given object in C, a sieve on C is a subfunctor of the functor hom C. This is the Yonah embedding applied to C. In the case of Ox, a sieve south on an open set U selects a collection of open subsets of U that is stable under inclusion. More precisely, consider that for any open subset V of U, sub will be a subset of hom U, which has only one element, the open immersion VU. Then V will be considered selected by south if and only if sub is non-empty. If W is a subset of V, then there is a morphism sub SOW given by composition with the inclusion WV. If sub is non-empty, it follows that SOW is also non-empty. If south is a sieve on X, and F(y)X is a morphism, then left composition by F gives a sieve on Y called the pullback of south along F, denoted by furs. It is defined as the fibered product S hom X hom Y together with its natural embedding in hom Y. More concretely, for each object Z of C, furs equal G Z y-fgus, and furs inherits its action on morphisms by being a subfunctor of hom Y. In the classical example, the pullback of a collection VI of subsets of U along an inclusion WU is the collection VU. Get ready for an exciting exploration as we unravel the mysteries of Grothendieck topology. A Grothendieck topology J on a category Celsius is a collection, for each object C of C, of distinguished sieves on C, denoted by J and called covering sieves of C. This selection will be subject to certain axioms, stated below. Continuing the previous example, a sieve south on an open set U in Ox will be a covering sieve if and only if the union of all the open sets D for which sub is non-empty equals U. In other words, if and only if south gives us a collection of open sets that cover U in the classical sense. Get ready to uncover the mysteries surrounding axioms as we navigate its intriguing terrain. The conditions we impose on a Grothendieck topology are: 1 base change if south is a covering sieve on X, and F(y)X is a morphism, then the pullback is a covering sieve on Y. T to local character, let south be a covering sieve on X, and let T be any sieve on X. Suppose that for each object Y of Celsius and each arrow F(y)X in sex, the pullback sieve FERT is a covering sieve on Y, then T is a covering sieve on X. T3 identity hom X is a covering sieve on X for any object X in C. The base change axiom corresponds to the idea that if UI covers U, then UIV should cover UV. The local character axiom corresponds to the idea that if UI covers U and VHJJI covers UI for each I, then the collection VH for all I and J should cover U. Lastly, the identity axiom corresponds to the idea that any set is covered by itself via the identity map. Welcome to the next segment, where we explore Grothendieck pre-topologies and its significance in our journey. In fact, it is possible to put these axioms in another form where their geometric character is more apparent, assuming that the underlying category Celsius contains certain fibered products. In this case, instead of specifying sieves, we can specify that certain collections of maps with a common codomain should cover their codomain. These collections are called covering families. If the collection of all covering families satisfies certain axioms, then we say that they form a Grothendieck pre-topology. These axioms are: 0 existence of fibered products for all objects X of C, and for all morphisms X that appear in some covering family of X, and for all morphisms YX, the fibered product XY exists. PT1 stability under base change for all objects X of C, all morphisms YX, and all covering families XX. The family XXYY is a covering family. PT to local character if XX is a covering family, and if for all XX is a covering family, then the family of composites XXX is a covering family. T3 isomorphisms. If F(y(x) is an isomorphism, then F is a covering family. For any pre-topology, the collection of all sieves that contain a covering family from the pre-topology is always a Grothendieck topology. For categories with fibered products, there is a converse. Given a collection of arrows XX, we construct a sieve south by letting psi be the set of all morphisms YX that factor through some arrow XX. This is called the sieve generated by XX. Now choose a topology. Say that XX is a covering family if and only if the sieve that it generates is a covering sieve for the given topology. It is easy to check that this defines a pre-topology. T3 is sometimes replaced by a weaker axiomatize identity. If 1x, XX is the identity arrow, then X is a covering family. T3 implies T3, but not conversely. However, suppose that we have a collection of covering families that satisfies PT0 through PT2 and PT3, but not PT3. These families generate a pre-topology. The topology generated by the original collection of covering families is then the same as the topology generated by the pre-topology, because the sieve generated by an isomorphism YX is Hom(x). Consequently, if we restrict our attention to topologies, PT3 and PT3 are equivalent. Now, let's shift our attention to sites and sheaves. Let Celsius be a category and let J be a Grothendieck topology on Celsius. The pair C, J is called a site. A presheaf on a category is a contravariant functor from Celsius to the category of all sets. Note that for this definition Celsius is not required to have a topology. A sheaf on a site, however, should allow gluing, just like sheaves in classical topology. Consequently, we define a sheaf on a site to be a presheaf Fahrenheit such that for all objects X and all covering sieves south on X, the natural map homom X, F homs, F induced by the inclusion of south into hom X, is a bijection. Halfway in between a presheaf and a sheaf is the notion of a separated presheaf, where the natural map above is required to be only an injection, not a bijection, for all sieves south. A morphism of presheaves or of sheaves is a natural transformation of functors. The category of all sheaves on Celsius is the topos defined by the site C, J. Using the Yonda lemma, it is possible to show that a presheaf on the category Ox is a sheaf on the topology defined above if and only if it is a sheaf in the classical sense. Sheaves on a pre-topology have a particularly simple description for each covering family XX, the diagram. Fax right arrow prod for in a fax alpha to prong right arrow top along right arrow top prod for beta in a fax galphatums XX beta. Must be an equalizer. For a separated presheaf, the first arrow need only be injective. Similarly, one can define presheaves and sheaves of abelian groups, rings, modules, and so on. One can require either that a presheaf Fahrenheit is a contravariant functor to the category of abelian groups or rings or modules, etc. Or that Fahrenheit be an abelian group, ring, module, etc. Object in the category of all contravariant functors from Celsius to the category of sets. These two definitions are equivalent. Turning our focus to the discrete and indiscrete topologies, let's explore its key elements. Let Celsius be any category. To define the discrete topology, we declare all sieves to be covering sieves. If Celsius has all fibered products, this is equivalent to declaring all families to be covering families. To define the indiscrete topology, also known as the coarse or chaotic topology, we declare only the sieves of the form Hom(x) to be covering sieves. The indiscrete topology is generated by the pre-topology that has only isomorphisms for covering families. A sheaf on the indiscrete site is the same thing as a presheaf. Get ready to immerse yourself in the world of the canonical topology as we examine its impact and relevance. Let Celsius be any category. The Yonda embedding gives a functor Hom(x) for each object X of Celsius. The canonical topology is the biggest, finest topology such that every representable presheaf, that is presheaf of the form Hom(x), is a sheaf. A covering sieve or covering family for this site is said to be strictly universally epimorphic because it consists of the legs of a colimit cone under the full diagram on the domains of its constituent morphisms, and these colimits are stable under pullbacks along morphisms in Celsius. A topology that is less fine than the canonical topology, that is, for which every covering sieve is strictly universally epimorphic, is called subcanonical. Subcanonical sites are exactly the sites for which every presheaf of the form hom X is a sheaf. Most sites encountered in practice are subcanonical. Prepare yourself for an eye-opening discussion on small site associated to topological space in the upcoming portion of this video. We repeat the example that we began with above. Let X be a topological space. We defined X to be the category whose objects are the open sets of X and whose morphisms are inclusions of open sets. Note that for an open set U and a sieve south on U, the set sub contains either 0 or 1 element for every open set V. The covering sieves on an object U of X are those sieves south satisfying the following condition: if W is the union of all the sets V such that sub is non-empty, then W equal U. This notion of cover matches the usual notion in point set topology. This topology can also naturally be expressed as a pre-topology. We say that a family of inclusions V a sub U is a covering family if and only if the union V equals U. This site is called the small site associated to topological space X. Moving ahead, let's uncover the hidden gems within big site associated to topological space and discover their significance. Let's be the category of all topological spaces. Given any family of functions U, the X, we say that it is a surjective family, or that the morphisms U are jointly surjective. If U of equals X, we define a pre-topology on SPC by taking the covering families to be surjective families, all of whose members are open immersions. Let South be a sieve on SPC. South is a covering sieve for this topology if and only if for all Y and every morphism F, Y, X inside, there exists a V and a G, Vx such that G is an open immersion, G is in sub, and F factors through G if W is the union of all the sets V, where F, Y, X is inside, then W equal X. Fix a topological space X. Consider the comma category SCAX of topological spaces with a fixed continuous map to X. The topology on SC induces a topology on SCAX. The covering sieves and covering families are almost exactly the same. The only difference is that now all the maps involved commute with the fixed maps to X. This is the big site associated to topological space X. Notice that SPC is the big site associated to the one-point space. This site was first considered by Jean Giraud. In the upcoming section, we'll be shining a light on the big and small sites of a manifold. Let M be a manifold. M has a category of open sets on because it is a topological space, and it gets a topology as in the above example. For two open sets U and V of M, the fiber product UMV is the open set UV, which is still in OM. This means that the topology on OM is defined by a pre-topology, the same pre-topology as before. Let M be the category of all manifolds and continuous maps, or smooth manifolds and smooth maps, or real analytic manifolds and analytic maps, etc. M is a subcategory of SPC, and open immersions are continuous or smooth, or analytic, etc. So M inherits a topology from SPC. This lets us construct the big site of the manifold M as the site M. We can also define this topology using the same pre-topology we used above. Notice that to satisfy PT0, we need to check that for any continuous map of manifolds X, Y and any open subset U of Y, the fibered product UYX is in M. This is just the statement that the preimage of an open set is open. Notice, however, that not all fibered products exist in MFT because the preimage of a smooth map at a critical value need not be a manifold. In this part of the video, we'll be diving deep into topologies on the category of schemes and unraveling its profound impact. The category of schemes, denoted ℓ, has a tremendous number of useful topologies. A complete understanding of some questions may require examining a scheme using several different topologies. All of these topologies have associated small and big sites. The big site is formed by taking the entire category of schemes and their morphisms, together with the covering sieves specified by the topology. The small site over a given scheme is formed by only taking the objects and morphisms that are part of a cover of the given scheme. The most elementary of these is the Zariski topology. Let X be a scheme. X has an underlying topological space, and this topological space determines a Grothendieck topology. The Zariski topology ℓ is generated by the pre-topology whose covering families are jointly surjective families of scheme-theoretic open emissions. The covering sieves ℓ are characterized by the following two properties: for all y and every morphism f, yx inside, there exists a v and a g, vx such that g is an open immersion, g is in sub, and f factors through g if w is the union of all the sets v, where f, yx is inside, then w equal x. Despite their outward similarities, the topology ℓ is not the restriction of the topology ℓ. This is because there are morphisms of schemes that are topologically open emissions but that are not scheme-theoretic open emissions. For example, let A be a non-reduced ring and let north be its ideal of nilpotence. The quotient mapper and induces a mapped spec and specker, which is the identity on underlying topological spaces. To be a scheme-theoretic open immersion, it must also induce an isomorphism on structure sheaves, which this map does not do. In fact, this map is a closed immersion. The étale topology is finer than the Zariski topology. It was the first Grothendieck topology to be closely studied. Its covering families are jointly surjective families of étale morphisms. It is finer than the Nis-Nevich topology, but neither finer nor coarser than the ℓ and ℓ topologies. There are two flat topologies, the ℓ topology and the ℓ topology. ℓ stands for, and in this topology, a morphism of affine schemes is a covering morphism if it is faithfully flat, of finite presentation, and is quasi-finite. ℓ stands for, and in this topology, a morphism of affine schemes is a covering morphism if it is faithfully flat. In both categories, a covering family is defined to be a family that is a cover on Zariski open subsets. In the ℓ topology, any faithfully flat and quasi-compact morphism is a cover. These topologies are closely related to descent. The ℓ topology is finer than all the topologies mentioned above, and it is very close to the canonical topology. Grothendieck introduced crystalline cohomology to study the p-torsion part of the cohomology of characteristic p-varieties. In the crystalline topology, which is the basis of this theory, the underlying category has objects given by infinitesimal thickenings together with divided power structures. Crystalline sites are examples of sites with no final object. Get ready for an exciting part as we dive into continuous and continuous functors. There are two natural types of functors between sites. They are given by functors that are compatible with the topology in a certain sense. Moving forward, we'll be taking a closer look at continuous functors. If C, J, and D, K are sites and U, Celsius D is a functor, then U is continuous if for every sheaf Fahrenheit on D with respect to the topology K, the pre-sheaf foo is a sheaf with respect to the topology J. Continuous functors induce functors between the corresponding topoi by sending a sheaf Fahrenheit to foo. These functors are called push-forwards. If C and D denote the topoi associated to Celsius and D, then the push-forward functor is US, DC. US admits a left or joint us called the pullback. Us need not preserve limits, even finite limits. In the same way, U sends a sieve on an object X of Celsius to sieve on the object X of D. A continuous functor sends covering sieves to covering sieves. If J is the topology defined by a pre-topology, and if U commutes with fibered products, then U is continuous if and only if it sends covering sieves to covering sieves and if and only if it sends covering families to covering families. In general, it is not sufficient for you to send covering sieves to covering sieves. See SGAIV3. Brace yourself for a deep dive into continuous functors as we explore its impact and relevance in our evolving narrative. Again, let's see J and D, KB sites and V, Celsius D be a functor. If X is an object of Celsius and R is a sieve on X, then R can be pulled back to sieve south as follows. A morphism f Zx is in south if and only if X is in R. This defines a sieve. V is continuous if and only if for every object X of Celsius and every covering sieve R of X. The pullback south of R is a covering sieve on X. Composition with V sends a pressheaf Fahrenheit on D to pressheaf on C. But if V is continuous, this need not send sheaves to sheaves. However, this functor on pressheaf categories, usually denoted V, admits a right adjoint V. Then V is continuous if and only if V sends sheaves to sheaves, that is, if and only if it restricts to a functor V, CD. In this case, the composite of V with the associated sheaf functor is a left adjoint of V denoted V. Furthermore, V preserves finite limits, so that adjoint functors V and V determine a geometric morphism of topology. In this section, we'll be deep diving into morphisms of sites, unraveling its complexities and uncovering valuable insights. A continuous functor U Celsius D is a morphism of sites D Celsius not Celsius D if US preserves finite limits. In this case, US and US determine a geometric morphism of topology. The reasoning behind the convention that a continuous functor Celsius D is said to determine a morphism of sites in the opposite direction is that this agrees with the intuition coming from the case of topological spaces. A continuous map of topological spaces XY determines a continuous functor OX. Since the original map on topological spaces is said to send X to Y, the morphism of sites is said to as well. A particular case of this happens when a continuous functor admits a left adjoint. Suppose that U Celsius D and V D Celsius are functors with U right adjoint to V, then U is continuous if and only if V is continuous, and when this happens, US is naturally isomorphic to V and US is naturally isomorphic to V. In particular, U is a morphism of sites. If you found this video helpful, give it a like and share it with someone who might benefit from it.